Right. I'm going to stay on the microphone because my voice is quite soft. So you heard Jeremy and about atmospheric correction, and you heard that atmospheric correction is a very difficult problem. One, because the signal from the ocean that contributes to total atmosphere signal is quite small, like 10% or less. And second, because the problem is fundamentally ill conditions. You may have different atmospheric states and ocean states in combinations that will give you the same type of atmosphere terms. So this is very ill condition. And there are a number of particularly difficult issues.
That's the first issue. Ok. Voilà, excuse-moi. C'est là où tu peux.
Okay, so there are a number of particularly difficult issues, and some of these issues that have not been resolved. And I'm going to talk about some of these issues, like absorbing aerosols, white caps, adjacency effects, and clouds and sunlight. And for a discussion of these issues and other issues, you may look at these kind of overview articles published rather recently in 2019 about atmospheric correction of ocean color imagery during the PACE era. But before we start, I would like to ask you a question based on Jeremy's talk. You probably know that I'd like to have your feedback. In your opinion, why is the ocean blue when viewed from space? You've seen these pictures from astronauts taken from the moon, from the space shuttle. Maybe you've seen some epic images. I'm going to talk about this epic sensor later from the L1 orbit. And you see this blue planet. And my question for you is why is the ocean blue when viewed from space? To be able to answer this question based on what Jeremy said. No idea? No clue. Remember, Jeremy said that most of the signal that you measure on the planet of the atmosphere comes from the atmosphere.
It's mostly signal from the atmosphere, like the scattering and the blue.
Yeah. So basically, why the ocean is blue when viewed from space is not because the ocean is blue, but it's because the atmosphere is blue and the ocean is relatively black. So it's something. It's important if you wish to. When you do ocean optics or atmospheric optics, you're kind of lucky in the sense that you can observe a lot of this phenomenon, and so you get to be curious about trying to explain it if you wish. And so this is an example. And you see the fact that if you misinterpret these kind of observations, if you wish, it can have some consequences for science. Let's say I'm going to observe some planets orbiting a star somewhere in the cosmos, and we may be able to do that in the future using spectroscopy, for example. And you you look at the planet, it's kind of difficult, of course, because when you have a star, there's always glare, so you have to eliminate that. It's complicated. But let's say you observe a planet via spectroscopy. You can say this planet is blue. You may say, well, there's ocean on this planet, there's water, but maybe completely wrong. So you have to be, it's important if you really be curious about these phenomena that you observe. Just try to go beyond if you need just simple equations, etc. Okay, let's start with absorbing aerosols. Okay, so what are absorbing aerosols? Well, they are particles that have an index of refraction with a non-null imaginary part. And that means that they are single scattering albedo, which is the ratio of scattering and extinction, is less than 1. And in fact, I'm pretty sure in previous lectures you saw the relation between the index of refraction and absorption. And there are two basic sources of absorbing aerosols, which are both of terrestrial origin. Industrial and natural. Industrial has a subcomponent of small particles, and you find these in urban type aerosols, pollution aerosols, and natural, like mineral particles present in dust aerosols. Two basic sources. And this is a simulations from a global transport model of aerosols over the globe. This covers a period of September to October 2006. And in orange, you have dust aerosols, in blue, sea salt aerosols, and green, you have biomass burning aerosols. And you can see the dust aerosol from Sahara. Here you have the Amazon burning at this time of the year, and also the South Africa region. There are also a lot of biomass burning. But what you see is that they are not just confined along the coast that one may think, but they affect very large areas, and they are lakes, etc. It's biomass burning here too, dust in the desert of Australia. So you see that the impact is really global. So you cannot just say, okay, I mean, the pollution, I don't care about these aerosols. Okay, now let's talk about how absorbing aerosol affect the signal at the top of the atmosphere. Well, first let's talk about aerosol scattering. We've seen that aerosol scattering affects the top of atmosphere reflectance at all the wavelengths, and in the standard atmospheric correction scheme, we use wavelengths above 700 nanometer, where the ocean reflectance is small or equal to 0, to basically separate the effect of the atmosphere or the aerosols. But the aerosol absorption influence strongly the top of atmosphere reflectance at ocean color wavelengths, especially in the blue and UV, and this is a major error for ocean color retrievals. Okay, and what's the cause of this? It's mainly because of the interaction between aerosol absorption and molecular scattering. And you can express the absorbing effect using this fairly simple formula. It's derived in this article by Omar Torres in JGR in 2002. And it's basically the product here of the absorption optical thickness. So aerosol is the total optical thickness, but if you multiply by 1 minus the single scattering albedo, you get the absorption optical thickness. M star is the air mass. You have a little contribution from the surface and the contribution from molecular scattering modulated by the location, if you wish, of the aerosols in the vertical. PA is basically the aerosol altitude or pressure. PS is the surface. So this is a basic formula that gives you what the signal due to aerosol absorption looks at the top of the atmosphere. And so this is these are just some plots of this equation that I showed before. So you have the absorption effect as a function of wavelengths here for different kind of aerosol, continental, urban, desert, dust, biomass burning. Some typical conditions here for the atmosphere. And the water reflectance is null in this case. And important to see is that in the near-infrared, there is very little effect. It means when you use this near-infrared wavelengths to estimate the aerosol reflectance, to correct the signal at the top of the atmosphere, you completely miss this effect due to the coupling between aerosol absorption and molecular scattering. And the effect can be large, as you can see here. Just have to have in mind always that the accuracy requirement for open color remote sensing is on the order of 0.001 and -3. You can see that these effects can be quite large, especially in the UV again. Why? Because you have more molecular scattering, so coupling is more effective if you wish. Also, you can see here the effect on the aerosol altitude. So there is a very strong dependence on aerosol altitude. And this makes the problem more difficult because aerosol altitude is a parameter that we don't usually determine from the remote sensing. And here is the effect as a function of air mass. Of course, air mass, you know what this is. This is just 1 over cosine theta s plus 1 over cosine theta n basically. Okay, so you have, of course, a strong effect in air mass here. So these are the basic dependence of this effect on the important parameters. And this is an example of problem that you can get by using a standard atmospheric correction scheme. We have the case of the dust storm of Libya here. This is Bowdoin imagery. And this is the aerosol optical thickness at 865 nanometer. And you can see that you have a quite large values in this region. And so this is due to dust from Libya. And this is the retrieved water reflectance by the standard algorithm. And you can see this kind of anomalous values here, low values in that region. The Mediterranean Sea is fairly hydrographic. You don't expect this kind of changes spatially. So the standard atmospheric correction strongly underestimate the water reflectance at 443 nanometer. Okay, now how to deal with absorbing aerosols. So one may try to detect their presence in some way. For example, by looking at some wavelengths where the water reflectance is known. For example, if you are in the open ocean, around 510 nanometer, the effect of scattering and absorption kind of compensate, and reflectance is quite constant. So you may say, if you do a retrieval by the standard scheme, you get something that is outside the expected range, you can say, well, okay, this might be due to an absorbing aerosol, and then you can shift to a different lookup table, more adapted to absorbing aerosols. What you can also do is to estimate the individual aerosol properties, which can be done using various techniques. What's important is, let's say the aerosol reflectance is basically proportional to the scattering albedo of the aerosols, the phase function of the aerosols, and the aerosol optical thickness. So you may say, okay, I'm going to try to estimate these parameters independently using different techniques. But one of the problems you have in this case is that the accuracy on the determination of these individual parameters may be too large to obtain the reflectance with sufficient accuracy. So I think in this problem, it's better when you look at this, it's probably better to try to estimate the signal more directly rather than the individual components of the signal. Third, while one may also use the entire information available, for example, spectral observations in spectral regions where the absorption effect is significant, like especially in the UV. And in this case, you may estimate simultaneously the key property of the aerosols and electrons by minimizing some kind of error criterion between the measured reflectance and the output of a radiated transformer. So these are some techniques that have been used. And you can, so this is what we can call a deterministic inversion model, but you have also statistical approaches that allow you to basically map the top of atmosphere reflectance to the water reflectance. So this is a third way, like try to determine simultaneously the aerosol properties and the water properties using all the spectral information available. And again, especially taking into account observations where the aerosol absorption effect is effective. Another way, if you look at, we'll look at that a little bit more later. If you look at the equation I mentioned about the absorption effect, you can see that it depends on angular geometry. So you may want to exploit this the dependence of the aerosol absorption effect on geometry and molecular scattering to estimate this absorption effect, especially, of course, in that case, you need multi-directional observations. This is an example of effect of absorbing aerosols. This is a sea waves and the Sea of Japan. In fact, we had some measurements during that day. In such measurements, and you have here the reflectance at 865 nanometer, and you can see a lot of white, which is the mask due to clouds, but not only to clouds, but also the standard processing masks regions which have a high reflectance above a certain threshold, but that also masks the case, for example, clear sky regions here, but that have quite a lot of aerosols. And this is the result of inversion using the standard algorithm here and a Bayesian approach. And you can see the difference between the two. You have here quite low values in these regions of dust, in fact, in many places. And if you look at the histogram of the values, this is the difference here between the two. So you see this kind of underestimation, if you wish, of the standard algorithm. This is the histogram of the values, and for the standard algorithm, you can see that you can have values even negative, but very much shifted to low values, while with this statistical technique, you get much higher values. And this is another example of this is the East China Sea. There was a measurements here, so the same thing. We have like quite a lot of dust here, and it's pretty clear. It's pretty clear day, but a lot of mask areas here because again the reflectance intensity parameter is too high for the standard atmospheric correction algorithm to handle. And again, the same thing as before. So you have the standard retrievals, and you can see this quite underestimation, if you wish. I would say lower values for the standard algorithm compared to the statistical algorithm. And here you have even more values that are negative. I did not put any negative values here, but you can see the shift here in reflectance. In fact, I mentioned that we have measurements, and so we could check whether, in fact, this statistical approach was better. And here you have the results, the comparison between satellite and in situ measurements with the standard algorithm and the Bayesian approach. And you can see it's not perfect, but it's certainly better than with the standard algorithm. So again, by using all the information available, even in the blue, not just information in the near infrared and then extrapolate, because you don't see the effect of absorbing aerosols. So by using all the information available, you can get a better approval. Now, I mentioned about angular information. If you recall, when you do the removal of this atmospheric scattering effect, let's say using a standard algorithm, what you're left is the ocean signal plus the absorbing effect. So, in fact, the signal that is remaining is the sum of the two, and if I use the expression before, I get this expression here. So that's an interesting equation, because you can see that the signal is really modulated by the product of the aerosol, of the molecular scattering and the air mass. And you can see here that if you regress rho TOA prime here versus m star rho molecule, and of course this depends on geometry, you can get an estimate of the water reflectance. Okay, simply because the extrapolation to zero air mass will give you directly the water signal. And I think with this kind of approach, what's interesting is you don't need to estimate the individual variables that govern the absorption effect, like the absorption optical thickness and the vertical distribution. So I think this is, again, that's what I said before, it's always better to estimate the effect directly than estimating the individual variables that govern the effect, because you have uncertainties in this individual variable. And these are some simulations of this here, T prime. They are divided by the absorption, by the transmittance by molecule versus raw molecule and star. And it's for different kind of aerosols. And don't spend your time reading this. And different aerosol altitudes. And the water reflectance is 0.02. And you can see here, by extrapolating the signal, for all the aerosol scale, aerosol altitude, you can see that by extrapolating the signal, you can get, you can correct for this absorption effect and get the actual reflectance, which is 0.02 here. Of course, something to notice is that the dependence is not linear, because these are accurate calculations. The formula show you calculations to approximate that. But you can eventually, I would say, linearize the problem by, let's say, using as a reference a typical aerosol solution. Right? And these are some theoretical simulations for the multi-angle atmospheric correction using MISER. I don't know if you know MISER, it's an instrument that measures in 9 directions. And so you can apply this technique to MISER if you wish. And these are theoretical calculations that show if you do a standard atmospheric correction for typical cases, and basically a range of cases in these statistics, for 46 nanometers, so you can get its huge errors, like 1 order of magnitude larger than the requirements. But if you do this correction, you can get into the range of plus or minus 0.02, which is acceptable. And you see, this is 46 nanometer, 558 nanometer. And this is an example of application of this algorithm to Polder imagery. Again, Polder is an instrument that measured in multiple directions, so you can apply this technique. So you have a case here of what you can see at 865 nanometer. You have this dust from Africa. Here, this band. If you look at the standard retrieval, you have like kind of lower values in this region. But if you use this directional method, you can get better results. So to sum, I would say again that determining aerosol parameters separately is an idea, but may not be sufficiently accurate to compute the aerosol reflectance and perform a suitable atmospheric correction. But that does not mean that it's useless, because you may be able to constrain the atmospheric correction or the retrieval using information about those properties. So again, it's still useful to, if you have information about single scattering albedo, about aerosol optical thickness, you may constrain the solution in standard type algorithm. Now, including the spectral observation in the visible may improve the atmospheric correction, and we expect further improvements by observing in the UV, and this will be the case of OCI on board the PACE mission. And also, the multi-angular information may be used to estimate directly the effect of absorption. And again, these individual variables do not need to be determined. So this kind of techniques have not been much developed, and hopefully in the near future with PACE, which also has a polarimeter with multi-directional observations. With this kind of mission, may be able to apply this. So again, it's not. These absorbing aerosols are not. The issue is not impossible to solve. There are some possibilities, okay? But they are not, I would say, being exploited fully so far. And I'm pretty sure they will be further exploited in the future. All right. So this is part one. The question about this. So we're going to talk about white caps now. Jeez. All right, white caps. So what is a white cap? Well, white cap is basically a mixture of air and water, right? Basically, when a wave breaks, it generates this foam at the surface, which are large bubble separated with a thin layer of water, and they inject bubbles into the water, small bubbles. And the white caps, they are white, so really reflective. So they enhance really the signal that you measure on top of the atmosphere. So even a small amount of white caps may be problematic for the retrieval of water reflectance. The problem is that the white cap properties like fractional area coverage, the spectral reflectance, are extremely variable, so difficult to model with enough accuracy. I've heard Jeremy talk about this, and this is a major challenge in ocean color sensing from space. And here, the enhanced reflectance in white caps is the product of the fractional area and the actual reflectance of the white caps. So this needs to be removed to provide suitable water reflectance estimates. So these are examples of seas with white caps. So you can see here heavy white caps, it's probably in the Southern Oceans and somewhere else. And frankly, when you look at an ocean like this, you just wonder, what can I do? Can I do remote sensing? And of course, I'm not talking here about bubble injecting into the water that affect the water reflectance itself, if you wish. I'm just talking about the problem of atmospheric correction, but there are many problems associated with a sea like this. And you just wonder, looking at this, I remember spending time looking at the ocean, some cruises in the Southern Oceans, and looking at that and saying, what's going on? How can we retrieve something reasonable from this kind of seas? All right, these are some measurements of the sea with and without whitecaps. This was done, in fact, very simply at the end of the scripts. We just put a radiometer in the surf zone, and so the waves are breaking, and no waves are breaking. And you can see this, so we had a very simple radiometer, a 4-channel radiometer. And we were collecting the data as a function of time. And so you can see these peaks here, with reflectance that can reach like 0.7, 0.8, so it's really reflective when you have these waves that break. So you see the signal without whitecaps is much lower, of course, like less than 10% in reflectance. But what was really striking is to see that at 850 nanometer, there was quite a difference. And our common sense, if you wish, I don't like to use this, but from our observations, we see that the whitecaps are white, say gray bodies, if you wish. And when we analyzed the data and we saw that, we were just wondering what's going on. Is the data good or wrong? So this points to something that you have to be very careful with your data. And the tendency when you have something like this is to say, oh, this is wrong. Especially if you look at when we made these measurements in the literature, the common knowledge, some people have done experiments in laboratory with whitecaps and showed no spectral dependence up to kind of 900 nanometers. And also models of whitecap reflectance did not show this kind of dependence. So when you have data like this, you can say, is my instrument working or not? So you have to be. So it's very important to make sure that you understand your instrument, the uncertainties that you have, to make sure that, okay, I can trust that this is an actual signal and not an artifact. So, and when you have something like this, then you just wonder what can cause this. And I remember spending a lot of time at the scripts here looking at the waves. What can cause this? Suddenly something came to mind, but maybe you can help me. I'll ask you later. All right. So this is about the variability of whitecap reflectors and fractional coverage. So these are after the work of I.D. Dearson. So you can see made much later a lot of spectral measurement, hyperspectral this time. And so you see the different shape and different level of reflectance depending of if you have so much bubbles, thin-film, residual whitecaps. And here these measurements by Whitlock I mentioned before, did not mention anything above any spectral dependence above 0.9 nanometer, but you can see in ID's measurements you have a lot of you really have a significant decrease in the near infrared of this reflectance. So this is for the reflectance, highly variable, and this is for the whitecap fraction. And you can see also it's just variable as a function of beam speed, which is used as a proxy for the fraction. So when you look at this, you just wonder how you can do some reasonable estimate of the white caps based on this measurement. So it just tells you that perhaps what we should do is to try to estimate the effect of white caps more directly. And so this is a simple calculation that shows the impact on the ocean floor, on the ocean color sensing of the white caps. Here, it's a simple model. The reflectance is a sum of, let's say, 4 terms: water, atmosphere, or aerosol molecule, and here the white caps. In fact, this term is 8 times the raw white caps. Anyway, in these calculations here, I use a rho A plus rho WC equal to 0.02, which in fact corresponds to an aerosol reflectance at 865 nanometer for optical thickness of 0.2 and typical scattering angle of a satellite observation. And when the white caps behave as a gray body and do the spatial correction, you basically meet the requirements for ocean color application, and this depends here on how far is the Einstein experiment. And here you have a different factor of the white caps on the rho A plus rho WCC. Okay. But if now the white cap reflectance varies spectrally, then you get huge errors and underestimation of the water reflectance, because again, you just correct too much because your signal is in the near infrared is lower than it should be, and then the spectral dependence changes. And you have this huge error. You see, it's an order of magnitude larger. So let's talk now about the reflectance modeling. So again, what can make this reflectance decrease in the near infrared? So again, I'm thinking by looking at the waves, finally we realize that what happens is that when the wave break and you have these underwater bubbles, they increase the scattering. And if you increase the scattering in a medium that is absorbing and more absorbing in the near infrared, you enhance the absorption. So that was kind of the revelation, if you wish. It took some time, so I have to say, to just think about what can, and also, as I said before, were the measurement correct or not, etc. So again, these bubbles increase the photon path in the water and therefore enhance absorption effects. So to capture this essential physics, one can model the white caps as a 2-layer system, each layer having a different spectral behavior. A semi-transparent foam layer at the surface, which corresponds to these experiments done by Whitlock in the early 80s. So term F form would say, and that depends on the amplitude. If you remember these plots before, the amplitude is quite variable, so this is something that you need to determine, and a spectral dependence that you can eventually take from this measurement. So, and then a bubble layer below the surface, which is characterized by its geometrical thickness, HB, and its optical thickness. Then you can express the total reflectance of the system as a function of basically the reflectance of the bubble layer, the reflectance of the surface tone. And this is a typical layer system, and you have interaction between the two layers, and this introduces some Cochlear terms here, right?
Is there a physical basis of construction for the equation?
For this equation,
That's just used to.
it's very simple. You have it's a
different way to make the radiative transfer equation simple.
Right.
And one of which is to build layers with different optical properties, and basically look at a stream of photons going down, and then a certain amount passes that in layer one, a certain amount is absorbed. And then what passes that layer goes to the next layer.
yeah, but this is yes.
This is, by the way, this is the most ecosystem model that include optics. This is how it's done. So it might be your importance in Galway, which is how light is done. It's still very massive. I don't think more of the acoustic goes on with it. It's done for the times.
That's a general one that is in purpose. Average.
But that's to do with how much comes from the trailer.
Exactly. So this is yeah.
It's reflecting back down.
This is a typical equation for two-layer system, and you can derive that by yourself. So using the properties and right, so taking into account interaction, it's a little times, it's a little series, and you get this term here. So you can, I'm pretty sure you can do this by yourself. All right. Well, in order to calculate this reflectance of the bubble layers, you need to have some kind of size distribution, phase function, and it's interesting. The phase function of the bubble have this kind of peak here. It's called a critical angle. This is where basically you have like total as a scattering angle increase. You have some total reflection on the side of the bubble.
So that's the notice is the power distribution of the bubble.
Right. Yes.
Is -4. It's a plastic film, which is the same as what you see in the part of the relation. And the break is the same as if you take a bottle and break it on the wall and those types of normal. They're -4. There's something in this -4 that's never magic. But it seems to work for aerosol, it seems to work for bubble, it seems to work for things that completely non-related.
Right.
And
okay.
the shelter, it's the one for all the years.
Right now, how to calculate? We can try to estimate the reflectance of this underwater bubble layer. So what we can do is use successive order of scattering situation. So you calculate this rho b, the reflectance of the bubble layer, the underwater bubble layer, as the sum of the contribution of the radiances at each order of scattering. And at each order of scattering, you have to weight by the probability of the photon to be scattered at this rate, right? So we end up with this kind of equation here, where the single scattering albedo is, of course, here the optical thickness of the bubble divided by the optical thickness of the bubble plus the absorption by the bubble layer. And here there is a plot of rho b as a function of power here. And what, these are the contribution of the different orders of scattering. And what you can see is that when you have, let's say, optical thickness that start to be large, I would say above 1. Let's say less than 1, a single scattering plays some kind of role, but above 1, single scattering does not play very much role. You have a lot of multiple scattering in the layer. And again, this is a way to visualize, if you wish, that because of that, you will have an increase of absorption and therefore a decrease in reflectance as a function of photons. So now when you can do this modeling, you can play, and this is the normalized reflectance, it's basically a spectral dependence for different optical thickness and the thickness of the layer. So, and by choosing these parameters, you can fit the measurements. So these were the measurements we did, and this is the surface reflectance, the reflectance of the surface form. This is the reflectance of the bubble layer. By choosing this parameter, the total reflectance, using this equation we discussed, you can fit the measurements. Now you can say, well, this is interesting. We have a model. Can we do some inversion? Maybe estimate this white cap effect from the imagery itself. So you have to of course, to observe in the near infrared, because this is also one of those ocean scenarios negligible usually. And here I selected the bands typical. That these are the OCI spectral bands to do this inversion from 865 to 12. So we have, so this is an example. So you have these different contributions here of the surface layer, the underwater layer, and the total. So we have some examples here. And this is an inversion using the measurements at those wavelengths. And you can see that you can, by spectral optimization, retrieve the white cap signal reasonably well. But this is at the bottom of the atmosphere. If you want to do something like this at the top of the atmosphere, you have more parameters to determine because you have the influence of the aerosols that you don't know. So the system becomes just too difficult to invert. Well, if you wish. So unfortunately, doing this from a mission using the OCI is kind of a difficult problem. You would need more wavelengths, but it would be possible, I think, if we have more wavelengths. But this is just an example of showing the four different configurations, so you can get a really good inversion. And again, as I said here, you have only 7 visible bands, so the inversion is unconditional in space, so you need more bands. But what you can observe also in this equation of ρB, the reflectance of the underwater layer, is that it depends on the single scattering albedo. So you may think about a modeling as a function of 2 extreme cases. A case of the surface form and a case of underwater layers. And using a mixing parameter here. And these coefficients here are basically a rewriting of the single scattering albedo. And so again, by choosing the case of underwater bubbles, these coefficients here, these alphas, are determined. And so this, you see that this allows you to reduce the number of variables. You now have 3 variables, or here you have 2 variables. You need to estimate this, and you need to estimate this P here, and be able to get the reflectance of the caps. Of course, you have another variable, which is the fraction of the surface covered with white caps. I would just add here that you see the signal of the atmosphere was maybe sufficiently smooth to be modeled with a few parameters if the wavelengths are properly selected. You've seen that the white cap reflectance, the spectral dependence, varies with the absorption, and it's really variable, so it's definitely not spectrally. But you may choose a few spectral bands where you can model this signal well with a polynomial with a few terms, for example. So this will allow you to do an inversion. So these are I would say, some ideas for the future to consider to try to deal with this problem of white caps. Now, some conclusion about white caps. From space, because the white cap reflectivity is high, even a small fraction of white cap within the field of view may be problematic, and which may lead to water reflectance error much larger than the requirement. And the white cap reflectance can be modeled reasonably well by assuming white caps as a two-layer system with foam on the surface and crane bubbles below. And the two layers have different spectral behavior, the underwater level, enhancing absorption. And again, this was the first hint we had at the beginning, why we have this decrease in reflectance. And we just thought that maybe it's because the bubble layer is so scattering that it enhances absorption, but the model can verify this assumption. Right. The model allows some good representation of in situ measurements, especially the spectral dependence, which again is the key parameter in ocean floor sensing, because you use an infrared. This is where the signal drops. You just extrapolate to the visible and just get large errors. Right.
The sensitivity of the bubble in the ocean changes with depth. If there's like a big bubble, much more boiling than a small bubble.
Yes.
Does that take it into account?
No, but I think the parameter, the model has sufficiently degrees of freedom, if you wish, take into account this. So other conclusions, listen. To repeat here, in the absence of atmosphere, you can invert the problem, but for space, for example, using the standard algorithm, you may still have to rely on some assumption about optical properties of white caps and their fractional convention. One may not be able to estimate them directly from the available measurements. So I think we're kind of stuck here for space, I think. So we have to be careful when you have high winds, etc. You have a question? But you have eventually algorithms that may be robust to white caps, like the polymer algorithm, because the perturbing signal, correct, is modeled to implicitly include the white cap signal. It's typically a polynomial with a term with a constant term, so something like constant spectrally. So this can represent a little bit the white caps, but not fully. But then you have other coefficients, lambda -1, lambda -4, that allows to take into account this effect. Okay, so that's it for white caps. Any questions about white caps? Yeah.
Usually,
It's not always a point, and there is a point in the white caps, but it's one within average because white caps is going to be on this. It's really sort of a relation. As I told you, it's so viable. But with the supercorrection of the illusion and the lines, yeah, it's not as you say, it's so viable. So I think this is a problem that has not been solved. Maybe we can think about it. Solve it.
How do you estimate the production of gas in this area itself? Well,
We said that the relationship between this part of the not fully developed different days, so. If they can actually practice, the video, the assumption is that. For the wings and bring the answer data. And that would be the.
As fully formed seed for a given was.
Exactly. Yeah, they were fully formed.
Yeah, it's you had another question.
I actually had a question on this slide. When it says they behave as gray bodies and there's smaller errors, and then with this, behaving the variance on the spectra, there's higher error. How do you do, like, is that a variation of the place that you're in, or whether or not it behaves in a gray body?
That would be if you assume that separately there's no it's what we call rhythms. Then the error is quite small. Whether you have small error, small large error, small errors, but if you want that perfect balance, notice as similar or A plus whatever you see. Yes, it's really going to be for a different time. Like the counts of force in the proportion of the labs. It doesn't look like it's pretty good. We have so depending on this, see the regions. We have from this software this mean. What's the weather together? So it's not about the weather outside. That's the all right. Are you okay to continue? Part number 3. Adjacency effects.
You take 5-minute break.
Sure.
Right. Okay.
I put a tripwire there from the. How long is that? Okay. So we have 15 minutes. But you're not starting at this. I just want to do small. Yeah. Yeah, that's the thing. Yeah. I'm taking some.
Light caps, there's depends on the water, I don't know. So we have a lot of effects on light. They got no.
Yes. Oh, it's a bit.
Is everybody back? So really the purpose of Robert's talk is just to expose you to advanced topics, like an enhanced, several advanced topics. And so you understand what are the kind of take up the art exposures, and we still need your generation developers there. But this is the positive side of this is that the community needs to, to help solve this. Right.
Good. So let's talk about adjacency effects now. Another big problem. Okay, what are adjacency effects? Well, they are caused by the atmospheric scattering of the radiance that originates outside the sensor field of view. So you have target here and you have the background, and photons may be scattered, reflected, scattered by the atmosphere, reflected by the surface, and diffusely reflected to the sensor, right? And of course, we are interested in this signal here. And these effects are especially important in the vicinity of land, but not only land. So it's not just the coastal zone, clouds, sea ice, but more generally, when the spatial contrast between the target and the environment is large. So, for example, you can be in an African region, so I'm going to show an example later on, and you can have large changes of reflectances over a few kilometers, and this introduces an adjacency effect. And they may here affect the retrieval of the water reflectance over distances of 10 to 20 kilometers. So it's quite large. And they are generally ignored in standard atmospheric correction schemes and operational processing of satellite motion telemetry. So you just have to be very careful when you look at some imagery in the coastal zone, because you may say, oh, some effects of gradients, maybe an interesting phenomenon. But be careful, because this could be due to the adjacency effects. This is an example of adjacency effect. This is where in Belgium, the Netherlands, and so this is some imagery at 865 nanometer, and you have a translate here. So reflecting so the complete pixel number here, and you can see as you approaches the land here, the reflectance increases, and this is attributed to the adjacency effect because you don't expect for this region, etc. Such a drastic change in aerosol activities. So this is the simulation of the adjacency effect at the top of the atmosphere. So you have the reflectance at the top of the atmosphere as a function of sun-zenith angle for a certain view geometry. And you have three sets of curves, one set at 380 nanometer, one at 500 nanometer, and one at 800 nanometer in red. And you have cases above land where the sensor is above land, where the sensor is above water, and the case where you have an homogeneous water. This is where you can apply this standard algorithm to model the atmosphere reflectance, what we've been doing for decades in this community. And you can see that the effect is can be quite large here, especially in the UV. This is in fact due to molecular scattering, and there are differences to other wavelengths. And this strongly depends on geometry. And this is for a target located at 5 kilometers from a linear coastline, right? And the sensor can be again over land or over the ocean. And so again, significant effects here. And also there are differences with the sensories over land, over the ocean, because the amount of, let's say, Fresnel reflection is different with the signals of the sensors over land or over the ocean. But there is very little effect on the degree of polarization of the light at the top of the atmosphere. So this is the impact, example of impact on the water reflectance retrieval. So it's important to notice that depending on the environment, which is can be, for example, vegetation, bare soil, ice, etc., the coupling between the surface reflection and atmospheric scattering may either decrease or increase the retrieved water reflectance with increasing rate. And you have an example here, the coast of Corsica. And here, this is the Beaufort Sea. So you have like some ice, here fractional ice. And you can see between the ice, you have these higher values of reflectance of 560 nanometer. Here, on the contrary, the values are lower. The environment is quite different. Here, you have ice. In fact, what you have is the ice is a reflectance that is fairly wide spectrally, visible to near infrared. But the coupling between ice reflectance and molecular scattering varies in lambda -4. So the coupling between the ice reflectance, and molecular scattering is a term that varies typically in lambda -4. However, you measure in the near infrared, you don't sense this lambda -4 dependence. So basically what you have to do is you underestimate the atmospheric correction. And this is where you end up with this higher retrieve water reflectance here. And it's different here because again the relationship between the contrast between vegetation and ocean reflectance is quite different. And here you have the high reflectance in the near infrared compared to the ocean. Oops. So now this is an example of impact on the chlorophyll concentration retrieval, and this is work by Center and Slishtish. You have retrieved chlorophyll concentration versus exact chlorophyll. These are from simulations. So this is for a typical contrast between land and ocean reflectance of 0.3 at 865 nanometer, 0.07 contrast at 670 nanometer. So it's typical of vegetation, I would say. And you have three sets of curves depending on the distance to the coast, 2 kilometer, 10 kilometer, 20 kilometer. And you can see that you may have, like if you look at, for example, these curves here are 2 kilometers from the coast, you can be completely off with respect to the chlorophyll concentration. The different sets of curves correspond to different atmospheric conditions. And let's see also geometry. So, but you can see the impact is dramatic. All right. And even at 20 kilometers from the coast, you may have still some effect. I mean, you don't have the one line is here, so you can see here this underestimation. So how do we try to deal with this? Right. So let's again look at the case of an homogeneous surface. This is called also the large target formalism, because in fact assumes that the target is homogeneous infinity. It's completely homogeneous, large target algorithm. So you have the reflectance at the top of the atmosphere is the sum of the reflectance of the atmosphere plus the signal from the water attenuated by transmissions, and this takes into account multiple reflections between the atmosphere and the surface. This is the typical equation that Jeremy talked about, except that it's formulated in terms of reflectance. Now, for an heterogeneous surface, you have to account for the reflectance of the environment. So this time, so this is basically, this corresponds to the signal that that arrives at the surface and that's reflected by the water body and transmitted directly to the sensor. And then you have to add this term which corresponds to diffuse reflection of different kind. And this is captured in this environmental reflectance. Here, you have to be careful here in my notation. TA corresponds to the total reflectance. There's often a confusion in the community. People confuse total reflectance with diffuse reflectance. The total reflectance is the sum of a direct term and a diffuse term. Okay, so just be careful because you will encounter different notation and it's confusing. So here I'm talking about the total transmittance, and here only the diffuse transmittance. And this ρe is some equivalent reflectance of the environment. So this is some kind of simplification, but I think it just gives you the essential physics of the problem here, where ρe is equivalent reflectance intervene. So therefore, the adjacency effect can be written as the difference between this ρt star in the case of an heterogeneous surface and a ρt in the case of the large target formalism. And you can see it's basically the difference between the equivalent reflectance, the water reflectance, and this is modulated by diffuse transmittance and total transmittance.
Is this a good stopping place for
Right. Sure, yeah, okay, no problem.
Pick up here at what? Okay.
Everything goes down.
I just. No more.
Yeah. So that, yeah, so you're asking, what already there is. No, we're looking at it from the, I was trying to learn I think anything that. Yeah. Yeah, they're all the same, underlying process. It's in a big- and it would be then- Yeah. Because the land you made it more. Spread or one. But that's not really. Yeah. Always.
I think it makes more sense. Oh, yeah, where?
We're getting there. Yeah.
Quand tu dois le convaincre, il faut des vite, c'est pas bien obligé.
Ah, mais
So, we'll go to what before the dinner. The visiting pond is a pond on the way to the office, okay? It's a great big screen. So, if you want to bring a suit to bring a towel, that's good basic stuff. It would probably. 6:30, the air from in the morning. And it's about, I mean, I'm kidding an hour. Now it's 10 and on. We get there. We get it around 10 a.m. We did it in 12. I'm telling you now. So, yes. It's not this way, not for school. But probably once you get there, there's no section. You're not all down off. So, Thanksgiving and that time here. Yeah. It's raining, you don't have to set them. The PC pond is on the way. You bring them and stop that and. Yes, PISCAY. The long arrow. Which we use for this very actually, it's very, very low. Now it's less. It's full of cigars to the point that you can't see the teeth. It can be used by the state as your dog. That's back goes in. Right.
Okay, ready to start? Okay, so again, this is the formulation of this adjacency effect. We have the homogeneous case, what we call also the large target formalism. And this is in terms of reflectance instead of radiance. This is the case where you have an heterogeneous surface, and just may want just to focus on this equation, which is the adjacency effect. That's the difference between an heterogeneous case and homogeneous case. And you see that this effect depends on the contrast between the water reflectance that you want to retrieve and some equivalent environment reflectance and modulated by atmospheric translucency. So, of course, the question is how to model this equivalent reflectance here. So it's basically so you have to take into consideration the spatial field of surface reflectance modulated by what we call the atmospheric point spread function, which expresses the contribution to the measure reflectance of photons leaving the surface at X and Y and scattered into the field of view. And of course, the target is at X equals 0, Y equals 0. So this is a very generic expression here. Now, if you want to try to simplify this, because this is kind of time consuming to to compute. So that you can make an approximation that when you have small viewing angle, there is some kind of a symmetry for the spread functions. So therefore, it becomes just a function of the radius with respect to the target. And therefore, you can then modify this and you get this expression here where instead of p, there is this function f here that appears. And this derivation is in this paper by Santerre and Smith. So you can look at that in detail. But okay, what's important here is to look at the dependence of this function f, and it can be approximated here as a combination of a molecular contribution and Fm and an aerosol contribution here. I substitute this P for aerosols and modulated by the diffuse transmittancy, weighted by the diffuse transmittancy. And these are some expression for Fm and Fp for a typical aerosol. It varies a little bit with the type of aerosol. This is for a typical aerosols. But it gives you some indication. So this is exponential functions of R. But this gives you, it's important to look at these equations because they give you some information about the spread, or let's say the distance at which you will have the influence of the environment. And from this, you get that, in fact, let's say the distance of influence due to molecules is about 12 kilometers, and for aerosol, it's about 1 kilometer. So basically, in this effect, you have a contribution due to interactions with molecules and interactions with aerosols, but the scale of the effect due to the molecules of aerosols is quite different. And you can see also here what's important is that these functions depend strongly on where the aerosols are in the vertical, which again complicates the problem when you have to estimate the aerosol altitude. Complicates the problem because you don't get this information systematically from satellite observations. Let's talk a bit about the variability of this adjacency effect. So, as I said before, it's produced by molecular scattering and aerosol scattering. Okay. And it varies with F and the reflectance of the background. The scale of influence is different. So Fm exhibits an exponential decay with a scale of about 12 kilometers, and Fp with a scale of less than 1 kilometer. So this gives you some idea of the type of influence. The scale of influence is adjacency effect. So, yeah, and in fact, theoretical simulations show that Fn is fairly constant with wavelengths. And again, the aerosol type change a little bit in Fp. And the spread, as you can see in the previous formula, the spread is larger if the aerosol is at a higher altitude. So now, how to handle the adjacency effects? So that's what we want to do. So one way to deal with the adjacency effect is to develop some atmospheric correction algorithm that minimize the effect. And one example is this spectral matching algorithm, Polymer. Some of you may have used it by François Steinmetz. and in which the atmospheric signal is expressed as the perturbing signal. It's expressed as a very simple polynomial with three terms here, a constant, a term in lambda minus 1, and another one in lambda minus 4. And so this allows take into account the adjacency effect. For example, if you remember, I told you like over this area with sea ice here, the Beaufort Sea, the fact that you have you retrieve a higher water reflectance, 560 nanometer, is due to the fact that you have a coupling between the reflectance of the ice, which is constant spectrally, and molecular scattering in lambda minus 4. But you see in this polynomial, you have a term in lambda minus 4. So you expect that using this kind of modeling, you will be able to take care of the adjacency effect. And this is an example. So if you remember, this was the example I showed you before with the standard algorithm. And this is what you obtain with the polynomial algorithm. So you can see that all around the ice here, the reflectance is much lower, right? Along the coast, so you are able to correct reasonably well with the adjacency effect. And again, so if you're not aware of this effect and you look at a standard product like this one, you say, ooh, really interesting, they have some blooms near the ice and blah, blah, blah. Or something different where actually there's less chlorophyll near the ice. An interesting phenomenon is actually, this is just an artifact of the algorithm that does not take into account the adjacency effect. So just be careful. Another example here is the Norwegian coast. You see that the standard algorithm this time gives you quite low reflectance along the coast. So you may say, oh, this could be an interesting upwelling type phenomenon or something like this. And you see also that in the inland waters, there is in this black. You have like this really just have too low values for 42 nanometer. But if you use the polynomial algorithm, you can see that the picture is quite different. You don't have these values anomalously low along the coast. And now you can retrieve something in a balance. So now another way to, so first way is to have algorithms that are robust to adjacency effects. But another way is to maybe correct systematically the top of atmosphere imagery for this adjacency effect at the level 1B and produce some kind of a level 1C. So that the processing of the leveling product can be done by assuming that the surface is homogeneous. This is some kind of an iterative process. And the simplest option, I think, which is easy to implement, and I think really the space agency should do that, is to correct for the effect associated with molecular scattering. Because if you remember the function f, etc., I mean, you know everything in this function. So you have the spread function, so you can really do this correction. And for the aerosol, it's more complicated, but of course, you get something more accurate. So you can use background aerosols and with approximation. You can estimate the aerosol property. And again, altitude is quite a challenge. And clouds, you can assume that they are at the surface, so you can estimate their altitude. So for these situations, in the case of aerosols, in particular, it's more complicated. But at least you can do this, which I think is really insidious effect in some ways, because you don't see it very well, and it goes over large distances. And this is an example of adjacency correction using this kind of iterative process. First, you estimate surface reflectors of the land over the ocean, and then you calculate using this kind of these functions the effect of the atmosphere. You correct the top of atmosphere signal, and then you iterate. And I want to show this example because it's in the open ocean where we think there might be this there's no adjacency effect, there's no land, it's clear, no clouds, nothing. It's an upwelling region, where it's off Namibia. So you have this is the region of the upwelling where you have a low reflectance at 4.3 nanometer, low radiance, 555 nanometer. And this is the effect of after correction, the impact of the adjacency effect. So you can see that you have changes by range from -4 to 4% at 442 nanometer and -1.5 to 0.5%. And the impact on the chlorophyll concentration is ranges from -10 to 10%. So this means that even in the open ocean, you may have some effects that are not negligible. So you gotta be careful again. It's just important to have in mind how difficult this atmospheric correction problem is. And when you have some imagery, just be careful in the interpretation, having in mind that there might be a lot of things that can affect the imagery that you get. And if here I have a variogram, the chlorophyll concentration as a function of distance. You know what the variogram is? Basically, it computes the average different square between pixels distant by a certain, which are separated by a certain distance. All right. And when you are at distance 0, maybe this means that you are everything is correlated. When this value increases, you have some decorrelation at larger scales. But this is what you have before, and it's what you have after. And so the spatial correlation is changed significantly. In fact, this suggests that less correlation here, so this an influence of the local processes is comparatively decreased at large scales after correction of the adjacency effects. So again, the message here is that even in the open ocean, the adjacency effects may be significant. Okay, conclusion about atmospheric correction in the presence of adjacency effects. So the adjacency effect can be important, not only in the coastal zone or in the vicinity of ice, sea ice and cloud, but also in the open ocean. Non-negligible under chlorophyll concentration. In our case here, the open ocean is almost 10%. And a change in the spatial structure correlation scales. And maybe a recommendation is that correcting systematically the level 1 beneath the adjacency effect is recommended. Recommendation. And however, when you have a coarse resolution sensors with a special resolution of 1 kilometer, since if you remember the effect of the aerosols is kind of confined to small scales, like 1 kilometer. So maybe it's sufficient to correct the effect, only to correct the effect for the molecular scale. And one would expect, of course, if you do this correction to improve the accuracy of the resulting imagery. Right. Any question about adjacency effects?
There's something that you look for That the dips are not as steady. Like how not.
It's something that's compared. That's so different. What will you the question was, how can you detect that you have a problem such as CNC effect in your pollution? I was just saying that you just can't because it's not a problem. It's so easy. But, in the coastal zone, you know that the effect can be important. I showed you actually these examples cannot completely different. So just be careful. But yeah.
You expected it was. The techniques is not changing. The business effect. It's only basically will change its problem. The goal is because what you're getting is put them down to the pixel nearly basically. The difference these are the basic.
All right.
How much does
I'm not sure. I think this is difficult to quantify because again you have to have insight measurements and compare the before correction and after correction. So I don't see very much of this in the literature, but this is something to check. However, we know theoretically, that the coupling between molecular adjacent to ice, we know that the coupling is in lambda -4. We know that we expect the reflectance to be higher than expected. So if now it's qualitative, if you wish, but it looks like polymer gives you more reasonable values according to what you expect. It's not quantitative. Again, quantitatively, you need to go. And so this is something that we'll have to do. All right, so more questions? And I showed some examples. You can see the difference. It's really striking. You can have quite a lot of difference. So just be careful. Yeah.
What's really
Maybe I will.
only that they're working on
All right.
We want to have that conversation. What's the purpose of the policy? Why? I don't know.
Well, I would say that all the atmospheric correction algorithms have advantages and drawbacks. That's something you have to know. Nothing is really perfect. Right. Polymer, I think, now we talk about this in the next, last part of my talk here. But polymer exploits something very important, which is that the perturbing signal that you want to correct is smooth spectrally. And that means that you can approximate it very simply with a polynomial or even with a few principal components. Right? So this simplifies the inversion. But in a spectral matching algorithm like polymer, the drawback is that when you are in a situation where the atmospheric signal resembles the ocean signal in terms of the spectral shape, you just cannot distinguish between the two. And this introduces some uncertainties. This is why I think polymer, if you look at comparisons with inside measurements, polymer tend to overestimate in the group. So this is the drawback of polymer, but there are other advantages, and the image quality is better generally than the standard algorithms. You can deal with paint, thin clouds, so you have like a much larger coverage of the ocean. So you have to put all this together and say, well, for my application, I prefer to use polymer. If I want to look at some kind of time series and changes over time, if I use the standard algorithm, I may have so many gaps. I can say anything about variability of the phenomenon I want to study. But if I look at polymer, I may have complete time series. So maybe this is what I should use. It's up to, but it's important to know, if you wish, to have in mind the different advantages, the differences in these algorithms, so they can do what they can. But I don't think you should think that any of the algorithms is perfect, especially in view of all these things that have not been taken into account. The problems, and okay, these are just some of the problems. Right, any other questions? Okay.
Just you can't implement yourself whatever atmosphere they are thinking of. So really, from people know that there's pieces. Not your but if you're reading, then you need to see that important. You need to look at the product. For researchers, we can
So another problem that, yeah.
And when shooting the taking of mistake algorithm, would you rather go, like I would go for one that's like just like when the macroscope is changing, but the spectral shape is the same, rather than one where the macroscope is the same, the spectral shape is the same, right?
So the question is about the spectral shape. I mean, if you're interested in spectral shape, if your algorithm is able to retrieve the spectral shape properly, it's okay, because it just depends on the algorithms you want to use the spectral reflectance with. If you want, for example, to estimate Frouin concentration with using a reflectance ratio, if you can preserve the spectral shape in the atmospheric correction algorithm, then you find. But it's another algorithm that's using the absolute reflectance, the spectral reflectance of the waves.
another point in the end, The only way we have to evaluate what is better is if we have something in or it might be the time series or the station of the world. Like, you always want to evaluate. It's the fact that you even do better, prettier, not. If you want something that agrees with that, with whatever it is you. That's the ultimate.
Actually, even a simpler version of all this. He called search for us. All it is, that's very against. Daily removal. And then caches. And there are a ton of forces out that knowledge that has search on signals. Pretty smooth. If you run like a line-based algorithm, especially with the magic right now, you have to flatten this a little bit. It's a relative understanding. It's with an application that very useful, which is usually like it's absolutely something sideways, you know, that with the medium, absolutely.
And I want to use the exploring, decide whether that is wrong or not in this area. Just talk with the others. They do that. From there, they can tell you if some changes along the reason, the reason, that's time to do.
And the other thing around there is it's steel away and pairing up with the property, and the PCA analysis, you have a correction. So that, you know.
It is number 4.
All right. Okay, clouds and sunlit. I mean, those of you who have looked at satellite ocean color imagery have probably experienced a lot of gaps in the products. And this is because it's generally admitted that ocean color can be observed from space only over cloud-free and sunbeam-free areas. And I think Jeremy emphasized this one. So in the state-of-the-art algorithms, the presence of a cloud or even a minimum amount of sunbeam prevents the utilization of the data. So consequently, what you have is like 15–20% of global coverage, and the wiki products show no information in many areas. So this limits the utility of satellite ocean color observations. You need typically global coverage every 3 to 5 days in the open ocean, and at least every day in the coastal zone. And do some scientific applications. So that's basically the status. And so these are some statistics of top of atmosphere reflection over the ocean in the near infrared. And this is, you have a cumulative histogram here on the left of the top of atmosphere reflectance at 862 nanometer observed by VIRS over the global ocean on 15 July 2018. And on the right is the percent of the VIR pixels selected by a threshold of 0.03 and 0.2 for this reflectance at 862 nanometer. 0.03 would be typically what the standard algorithm would do to eliminate glint, bars, etc. If you look at the cumulative histogram, you can see that when you have this level of reflectance, 0.03, what you get is very few observations during the day. However, let's say that you could eventually do the atmospheric correction problem up to 0.2 for the total atmospheric reflectance in the near infrared. This would be this curve. You see that you would increase coverage substantially for example, in these equatorial regions, and you go from almost 5% to 35%. Here you go from, no, no, here at the equator, you go from 15% to 55%. So that's really significant. Of course, the question is, can you do this? Let's note that, let's say for a cloud of albedo 0.2 flux, you have 80% of the photons that are incident at the TOA or at the top of the cloud layer. They may reach the surface, but the transmittance is basically 80%, 0.8. And then on the way back, you have 80% of the photons reflected by the oceans are transmitted back through the layer. So that means the transmittance along the double optical path through the cloud layer is 64%. And this is quite large. That means that the signal measured at satellite altitude should be sensitive to interactions and therefore to the characteristics of the water body. But I'm saying here is that the problem is not completely lost when you have a cloud of particles of albedos. Still have photons that have reached the surface, interacted with the water body, and that came back through space through the clouds. So you have information about the water body, right? So these are some examples of radiative transfer simulation of the top atmosphere reflectors for a black water body. You have here simulation with the glint and outside of the glint for different type of aerosols, different aerosol thickness. So as we've seen before, as Jeremy has pointed out, the perturbing signal results from many processes and couplings, and it's difficult to model accurately. But as I said before regarding polymer, what you can see is that the signal is smooth spectrally. So this is very important. So therefore, the perturbing signal can be represented by a polynomial or linear combination of orthogonal components with a few terms of eigenvectors, and so you can linearly express the, let's say, the rho p here is the perturbing signal, the corrective signal for molecular scattering, whatever. Actually, you don't even need to correct for molecular scattering. You can still decompose the signal also. And usually, 3 or just a few terms are sufficient to represent correctly this. So in the spectral matching, as we've seen, they make first some correction for molecular scattering and some average glint, because you never know exactly what is the glint signal. You use the wind speed, which is something that comes from some realistic data. It's totally accurate. That's not sufficient to correct the glint problem. So they do some kind of average correction, but you end up with a signal that is smooth spectrally that you model with it. Now, in this other atmospheric correction algorithm based on the principal component analysis, basically what you do is you decompose the signal at the top of the atmosphere into principal components. And then you select the principal components of the top atmosphere signal that are correlated to the principal components of the water reflectors, right? So this, in fact, is an atmospheric correction because you just eliminate the principal components that are sensitive to the perturbing signal. And so this allows you to reconstruct the marine reflector. So basically you have this decomposition in principal component at the top of the atmosphere. And you also decompose the signal at the bottom of the atmosphere into principal components as well. And again, here you need a few components to reproduce the signal properly. And then you do some kind of mapping, you select these CPIs, and you do the ones that are correlated to the auto-reflectance, and you can do that in an ensemble of simulations or observations before applying the algorithm operationally. And so this allows you to get these principal components here. And once you have that, you can reconstruct the auto-reflectance, right? And this is an example of a polymer retrieval. Mary's 21 June 2004, North Atlantic. So you have here an RGB composite, the scene of Portugal. Portugal here. So you see all these clouds, you have glint in this part of the area. So this is typical of Mary's. You have thin clouds, etc. So it's a very noisy image. But with the polymer algorithm, look at what you get. You're able to get retrieval in the glint area when you have thin clouds, except when the clouds are too thick, you cannot do anything, so you have to mask. But with a standard algorithm, most of this image will be masked. And interestingly, here you can see this is chlorophyll concentration. So you have these high values of chlorophyll concentration. And this is a known phenomenon which occurs at the shipwreck due to the interaction of infrared waves with the bottom. And so this is well known. Of course, you can see anything here in the RGB. And so it's just amazing that you can retrieve this kind of signal in some imagery that are influenced by so much glint in clouds. So I don't know, but to me this is kind of convincing that you really see, you really can do this problem in the presence of glint in clouds. And if you look now at the impact on the global coverage, so this is the typical product for like 1 day, global imaging using the standard algorithm, and this is what you have with polymer. And again, I'm going to go back to this image. I forgot to mention, I mean, we don't see any artifact at the edge of the clouds or at the edge of the glint. It's continuous here. So it's a very good demonstration of what you can do by using this simple property, I would say, that the signal is smooth spectrum. Right, so you see the increase of coverage that you may get using this polymer algorithm. This is another example in the Arabian Sea, where you have here a 3-day composite, June 3 to 5, June 2023. So this is the Mary's algorithm. This is the Modis product, and this is the Mary's using polymer. So you see that with polymer, you have basically you're able to basically complete coverage of this area, with the coastal area, and everything, while in the standard algorithms. Because again, you are very conservative with these algorithms, and so you eliminate a lot of data. But again, there is a need, so I think people should be interested in pushing the envelope here and try to see if they can do something below the clouds in the presence of glint. And this is the same example of Portugal I showed before, but this time using this PCA-based algorithm. So this time it's water reflectance at 443 nanometer. And you can see again that you can really mitigate the clouds, the thin cloud and glint effects. And this time here, you remember we had this high chlorophyll concentration in this region, where here now you have low reflectance. Of course, low reflectance in the blue means more chlorophyll concentration. So this is consistent with the previous image, but here we detect also something a bit different, which is a very reflective species at 4.3 nanometer, and this may be due to, in this case, it may not be performance. So again, two different algorithms that show for a very complicated image contaminated with clouds and glint that you can do the problem reasonably right here in this kind of situations. So it's kind of encouraging. This is also another example with the PCA-based algorithm. This is the Arabian Sea, so you have the reflectance at 865 nanometer, which shows the clouds. And this is the cloud mask with the standard algorithm, but this is what you can retrieve. You don't need a mask with the PCA algorithms, and you have the reflectance and the chlorophyll concentration. Now, recently, some work has been done by Joanna Joyner and some other people about this problem, trying to retrieve water signal in the presence of clouds and glint. And what they try to do is just do some kind of mapping between the PCs of the TOS signal with the surface reflectance, and then the chlorophyll concentration. And what they do is they use Frouin, which is an instrument which has a relatively coarse spatial resolution. And she's basically training her machine learning technique using concomitant MODIS and troponin observation. So, and because this difference in spatial resolution, you can have correspondence if you wish. Because otherwise, you would not be able to see anything below the class if you just use MODIS. So you could do that, for example, to do the problem for MODIS, but for troponin it works, and you have here an example of retrieval with a plus standard, so you have a lot of gaps, and with troponin, daily you just have very little gaps, and no noticeable contamination from something, which is something. So what are the conclusions about atmospheric correction in the presence of cloud and sun? So I would say that atmospheric correction can be performed through thin clouds and in the presence of sun glint, polymer, PCA-based machine learning algorithms. They have put some examples. They have shown that they can deal with this problem. And spatial continuity is good, and the daily coverage is increased substantially. Yeah, Problem, however, with this machine learning technique based on satellite retrieval is that the satellite derived products are the reference. So, of course, if you say my reference is the Modis derived chlorophyll, maybe you have to be sure, but derived by the standard product, maybe this is a problem. So you have to be careful with it. And so you expect by increasing this coverage to really get important new information about the temporal variability of biological processes. So again, this is not an open problem. So you always to try to look at these things, and even if it's kind of strange. For example, you are on an airplane and you look at it's cloudy and you don't see the surface, and you say, well, I don't see the surface, there is nothing I can do. But now if you think a little bit more and say, well, okay, but if this signal is constant, maybe I can retrieve it if I have enough sensitivity, and that could be sufficient. So try to think kind of beyond what you usually get. Okay, these are some issues, but that's not the end of the problem. There are other issues. I don't have time to talk more about talk a long time about this, but the other issue is radiometric calibration. Of course, I think people talked about this before. You measure a signal at the top of the atmosphere that you can calibrate absolutely to a couple of percent, but a couple of percent at the top of the atmosphere means about 20% in the bottom of the atmosphere. So you can see the kind of uncertainties that you may have. So you need to deal with this problem, and usually this is using what they call system backwards calibration, where you basically backwards your calibration coefficients by applying the atmospheric correction algorithms in place where you have signals like moving. Correct. Now, something that we neglect also is the spatial heterogeneity of the atmosphere. You measure at 60-degree angles, 70-degree angles. The sun is at 75 angles. Another problem is the aerosol altitude. I mentioned that before. The aerosol altitude is very important to correct for absorbing aerosols. But it's also important even to know, even when the aerosols are not absorbing, we should use some parts about this later. And another thing is the Earth's curvature. We know these algorithms to assume that the Earth is plane parallel, but actually there is sphericity, and this changes the signal that you measure. That you model the top of the atmosphere if you compare it to the and also there are some other problems. Again, it's the separation of the signal, the UV. People say we're going to the UV because in the UV you are more sensitive when you see an absorption, which is true. But when you are in the presence of aerosol absorption, the effect will be similar, and again, may not be able to discriminate them. So just a few more curves. All right, so here I just want to illustrate the effect of the aerosol altitude in all the schemes so far. This is neglected. I'm talking about the effect of aerosol altitude basically the standard scheme, you use an aerosol scale height of 2 kilometers and you generate your lookup table like this, and then you do the correction. But here I should have coupling term due to interactions between aerosol and molecular scattering for non-absorbing aerosol. 1998, tropospheric 70%. Yeah, for different scale, aerosol scale heights. And this is a function of geometry. Solar zenith angle is 36 degrees. Right. Optical thickness 0.1 and 865 millimeters. So typical conditions. And what you can see is that the differences here, the kind of differences that you can get depending on the geometry, and this is probably due to accidents in the phase function. You can have differences of several 10⁻3. In this case here, it's even larger. You can have differences between different altitude of an order of magnitude. So this is in the case where, just due to multiple scattering interactions between aerosol and molecular scattering. So it's not a negligible effect. And I think we have to know this and then to try to correct if we can. But the problem, of course, is how to estimate this aerosol altitude. But in new satellite missions like PACE, aerosol altitude is a variable that's going to be estimated. So this is maybe an opportunity to take this effect into account. Right. First curvature. So this is a simulation, the ratio of the Rayleigh reflectance at the top of the atmosphere, just molecules, calculation in plane parallel and calculation assuming Earth sphericity. So you can see that the ratio decreases really rapidly for this is considered here. This is a function of the solar zenith angle. This is for different view zenith angle. I think the relative azimuth angle is 90 degrees in the simulations. And it's not so important because Rayleigh scattering is kind of stuff like very much directional. But you can see that above, let's say 70, 78 degrees or something, you start to have like really important decrease. Okay. And you just have to have in mind here that we want accuracy on the water reflectance of the order of 10⁻3, and it's a fraction of 1%. And definitely you're not going to get that if you don't compute accurately this Rayleigh reflectance. For those angles, the impact is really important. Of course, usually we don't do atmospheric correction for these large angles, but if we want to, I don't know if you're interested in high latitudes, expand the validity of the products to these latitudes, then you would have to do this kind of thing. But I would say more importantly is to look at what happens at small zenith angles. See, that's what we don't see very much here in these simulations, but at small zenith angle, we have like solar zenith angle 0 to 80. So yes, the impact is start to be significant in this range, very significant. But at the small angle, zenith angle, you see that you may have ratios that are different from 1 by a function of 1%, like 0.4% or 0.5%. But again, what 0.1 plus 1.5 plus what 0.5% mean is 5% error at the atmosphere, at the bottom of the atmosphere. So again, I think it's important to take this into consideration. I think this is something easy to correct and probably sufficient to just compute the lookup tables for various categories, assuming that you have a spherical shell atmosphere. And finally, this separation of CDOM and aerosol absorption in the UV. These are some examples of the CDOM absorption effect at the top of the atmosphere for some different, I guess, CDOM absorption here and here. So this is the CDOM absorption effect for some chlorophyll, for some CDOM slope of the absorption coefficient, and some geometry. And this is the aerosol absorption effect I mentioned before as a function of wavelengths for different aerosol altitudes. And what you can see is that the CDOM absorption effect is quite similar, especially for 0.1. It's just very similar to the aerosol absorption effect. So that means that it might be quite difficult to separate these two effects in the presence of storms or in aerosols. All right. I think that's it. Any questions? Questions about the magic of atmospheric correction?
So that we move the attic clock to tomorrow. What is the attic clock? Yes, I will do tomorrow. It's supposed to be tomorrow.
I was supposed to be a talk about EPIC. I don't know if you heard about this mission Discover from the L1 orbit, where you have this beautiful James Webb telescope, but you also some instrumentation to view the Earth. And I would like to talk to you about this because there are a lot of potential for temporal sensing. And we could say that maybe in the future, NASA will consider an ocean color mission from the L1 orbit, but we'll talk about that more. Okay. Questions?
So when now is in that.
We have a dental break prepare for tonight.
Break tonight.